this oblique path a detailed picture, because you need to do some simplification to estimate where is this electron density which you get from this path. Furthermore, there is this complication when you are at the altitude, higher altitudes, that the ionosphere is very structured, and the auroras are causing there some rapid variations and structuring, like I explained to you. So what we have been thinking in Finnish Meteorological Institute, and we are doing here also close collaboration with the Oulu University, is that we need also other type of satellite measurements to support the GNSS observations. And here is the concept which we are currently developing. In addition to the GNSS satellites, if you are looking now the left-hand panel there are the oblique GNSS signals coming from quite far away. In addition to that, we have satellites which are in polar orbit, and they are at lower latitudes, lower altitudes, so roughly in the altitudes of, let's say, 400 to 800 kilometers. Polar orbit, circular orbit. These kind of satellites, they kind of very fast pass over the network which we have here. We have in the middle panel you see actually a map, and you can see there is plenty of dots. The blue dots are actually GPS networks, what are operated by national mapping authorities in Finland, in Sweden and in Finland. Actually in Finland we have two quite nice networks. The light blue dots are the Geotrim network, so it's a commercial operator, and the purple dots are the land survey, Finnish land survey receivers. But in addition to that, we have a few stations which are not so nicely visible, but let's say some 6 to 8 stations in different latitudes along the Finland. The most northern stations is actually in Svalbard, where we have these beacon receivers. And these beacon receivers are receiving radio transmissions with frequencies of 150 and 400 megahertz from these polar orbiting satellites. And this satellite is kind of going past through the network, like I said, and then the signals come very nice in different elevation angles and scanning through the whole area. This type of signals are necessary if we want to do the studies of the ionospheric structure in a tomography method. And so we are in our system, we are combining the GPS signals, which are more or less available all the time, but they have this problem of oblique paths, and to support them, then we have every now and then the beacon transmissions from the LEO satellites. But the problem with the beacon satellites is that they are available only a few times of the day. Okay, so, but in this slide I kind of try to summarize what are the good points and what are the challenges in this approach. So I'm talking about tomography. So we are trying to do the same thing as they are doing if you have a for example, if they are doing magnetic imaging of your brains, like in the upper panel. Compared to the upper panel, we unfortunately don't have so nice coverage, so we cannot illuminate the ionosphere from all directions like they are doing to the patient who is lying there. So the problem is a bit difficult to solve. And then we need to support from some other instrumentation still to make it some kind of first guess about the structure of the ionosphere, so that the problem, which is very badly ill-posed, can be solved somehow. With the ill-posed problem, actually, what I mean is that we have several unknowns. We have actually the kind of the grid, with the grid points, three-dimensional grid, and the electron densities, they're kind of unknown in each grid point, and then we have the measurements only along certain areas, along the satellite track, or then the integrated along the GPS signals. So we have kind of less information than we have the unknowns, and then you need to do certain tricks to solve the problem. But the inversion method which we are currently developing, there is some nice ways to solve these problems. And it also allows a systematic error estimates for our results, which is not at all true always when we are doing ionospheric research. And it is based actually on cheap technology. So these beacon transmitters, they are quite easy to build. I'm sure you could build these kind of transmitters, and they are kind of commercial off-the-shelf technology, and they have been tested in CubeSats, at least in some missions. So we believe that when now Finland is moving to the satellite area, in the sense that the Aalto University is building and launching these nanosatellites, so maybe in the future sometime we can put one of these beacon transmitters also to these CubeSats, and then consequently we would get these measurements with cheaper price more often than today. Okay, and yeah, okay, I said briefly that so we need some support for this approach, and one instrument who can provide us support is the ionosomes. So this is probably a familiar instrument for you. It is kind of based on the fact that particularly in the HF range, the radio signal is kind of reflecting back from the ionosphere, and if you are doing a sending using different HF frequencies, you can measure how long it takes from the ionosphere, how long it takes from the signal to go to the ionosphere and come back, and from that you can deduce the structure or the altitude profile of ionospheric electron density. So this is an independent measurement, and it can be used to support the tomoscan measurements. And then another independent way to see how good our results is to use high power radars. This is a bit expensive way to do it, but every now and then we have measurements by these ASCAT radars, which is a radar system operated as Northern collaboration. So the host countries are Norway, Sweden and Finland, and there are also some other countries in the association like UK and Japan and China. And with these high power radars we can measure also the electron density and other parameters in the ionosphere. And in the future we hope that we can upgrade this system even so that it is not just along one beam of the antenna where we can measure these parameters. Instead we would have a system of phased array antennas, and with these phased array antennas we could create a volume in the ionosphere where we can measure the ionospheric particles, so properties, so not just density but also temperatures and velocity of the plasma in this volumetric area. And then this is my kind of last slide. In FMI we always need to think what is the kind of the relevance for society, for our research, and for ionospheric research. One motivation is, although it's very sad, but it is true that the global warming is opening new shipping routes in the Arctic area, and when you are in the Arctic area you have this disturbed ionosphere, and then you have also this situation that GPS is not maybe always so nicely available, or you want to use HF communication from ship to ship, for example, then it is important to know the structure of the ionosphere, particularly for the HF communication from ship to ship, and also particularly US civil aviation, so big air companies are planning also to have polar routes. So also for this aviation, this HF communication will be important in the polar areas. So we hope that maybe in the future we could use this tomoscan type of probing systems to support, for example, the communication between ships in the Arctic region. Okay, and this is all what I had in mind, and now I can try to answer your questions with my best effort. Thank you.
One question about this predictability about this phenomenon stirring in the ionosphere. So, if you have a capability of scanning and basically getting the understanding that what is the current status, how predictable this is in time scale in the future? So, can you make any kind of predictions that what is happening in next day?
That's a very good question, and that is actually what we hope that we can do. Currently, the physical understanding is not yet very good in this phenomena. So we can do forecasts maybe 1 to 2 hours ahead. But if you are asking the situation for the next night, for example, if you on this ongoing night you see that there is disturbances, and you want to know whether they last for the coming night or so, that's still very, very difficult. If you want to do this very carefully, then you should have this a very good physics-based model. And I said in the beginning already that the ionosphere is difficult to model because it is interacting with a neutral atmosphere. So it's not only about physics, it's also about chemistry and dynamics and so on. So it is challenging, and these models are currently quite consuming also in the computation time. So challenging, but hopefully we will be able to do that in the future.
How much is computing, how much is practical work? 50 or?
What do you mean in practical collecting? Yeah, okay. I think it is the computing is now taking most of the time. Yeah. So it is kind of a collecting the data routines, collecting them is kind of, once you get the routines operating, that's quite automatic, but then it just takes the computing time, takes quite long.
Yeah, there was a picture or a photo of these ASCAT antennas in the slide. Especially, it was second to that one. I'm interested in this ASCAT VHF antenna. Where is it located?
It is in Tromsø, in Tromsø, yes, Norway. Yeah. Size of a football field.
So it's a transmitting.
Yes. And it is actually, it can be split, kind of split into 2 parts. So it can do a bit kind of in 2 directions. This technology with these big antennas is now kind of going a bit away, and we are now moving more to these phased array things.
Is there a way that I would say the community or even hobbyist community could actually support measurements in a way, because some of us have quite a bit of receiver base here and there, and actually deploying it, for example, even SDR-based receivers is actually getting quite cheaper nowadays. If you think of what present day chip design is, the price of actually building up receivers and that can be also even synced into, say, GPS or GNSS, other GNSS systems, so that you have even time-locked measurements if needed. Would there be a need for that, or is it just that you want to keep the science yourself, so to say?
No. Actually, yes, we are very interested to collaborate, and actually, we are a bit behind. The astronomers are using also the amateur society very efficiently and getting very good results in this collaboration, and we should learn about that, and certainly exactly like you say. So for example, these beacon transmitters which we currently have, so the transmitters are not very expensive, and the receivers are not expensive, and they are quite easy to build. And actually my colleagues in Oulu University, and particularly in the Sodankylä Geophysical Observatory, they are very eager in building new solutions based on these soft radio solutions and everything. So they are planning, for example, to do these ionospheric measurements. They have ionospheric, but you can make also oblique measurements. So you could have a cheap receiver and observe this signal what they are transmitting from several places in the Finland, and this way you could use also this type of measurements to probe the 3D structure in the ionosphere. We should do more close collaboration in this.
Thank you.
Thank you.
Thank you.